how's everybody doing? So assignment 1 is over, deadline expired. So when I asked you guys about this in class, everybody seemed to be saying it was going okay. I asked if you were working on it, everyone nodded their heads. Maybe that's true for the people in the class. In general, there seems to have been some people who waited a little bit late. You can witness this by, for instance, the explosion of messages on the student forum the weekend the assignment was due. More in those 2 days than on the entire previous month of the course. So I guess not everybody in here was honest, or the people who waited till the last minute were not in this class. That's okay. Hopefully it all turns out right, okay for you. The TA is very generous. He wrote a script that goes back and looks through every submission that you made, finds the highest mark that was recorded out of any of those, and that becomes your grade for the assignment. So the grade from that process is the one that gets posted on CU Learn. The ones that you get mailed or whatever, they're not, I don't know, they're not the official ones, I guess, unless there's some dispute. Okay, good. Working with the assignment server is helpful, unhelpful, painful? Helpful, good. I mean, the alternative is you get absolutely no feedback and you submit something to a TA who's going to mark it, and then you'll find out what your grade was a couple of weeks later. I don't know, I like the submission server better, but not everybody does. And don't forget, assignment 2 is up now. Start working on it. Submission server is not up for it, but the assignment itself has some, sample sort of lousy testing code included with it, so you can at least get started and get going. All right. Today we're going to spend one day on a topic that is, interesting enough, but you see it in other places, and that's linked lists. So far we've studied lists implemented as arrays. That's one extreme. The other extreme are the so-called linked lists. So I guess a bunch of you are taking something like Comp 2401 as well. Yeah, are you doing linked lists in that course? Not yet. You will get there, and you'll get a lot of it. So we'll just do it quickly here. Linked lists take basically the opposite approach of what array-based lists do. So array lists basically take one giant chunk of memory, and that's where all the list items go. It's that big array. Linked lists actually break up the list into each element gets its own little piece of memory, and so each element gets stored in something called a node. And a node has two things, basically some data. This is the data that's stored there. And it has some pointers. And so I will say start with the simplest thing, which is a singly linked list. This is what a node looks like. Okay. Does this definition of a node bother anybody? No, it's all good. So a node contains data, we'll call it X, and it contains a node, which we'll call next. That should seem bothersome unless you've been programming in Java for a while, in which case you know that this thing here is just a reference or a pointer to another node. So that's not a problem. So really a node looks like this. There's a place over here where the data goes, X, and then there's this next thing that goes here. And this is a pointer or a reference to another node. Okay. So that's what a node looks like. And if you're working with a singly linked list, there's a few things you can do with those. One thing you can implement with a singly linked list is a stack. In that case, you need to have basically one variable which keeps track of the top of the stack. So a stack has a variable called top. It is a node, and it points to the top thing on the stack. So this is what a picture of a stack implemented as a singly linked list looks like. There's a bunch of nodes. Each one is linked to the next one. The top node has a reference to it contained in this stack object. Okay? So what do you do with a stack? Well, there's two operations. Push. So if I want to push something onto the stack, what does that look like? So I want to add a new thing to this stack. So what should I do? Yeah.
Create a new node with the value of it being x and the next node being
So we create a new node, let's say t. It contains x. So we'll draw that here. This is our node t. It contains x. And you say, let's set the value of t, the pointer in t, to be the top of the stack. So that does this. And now what? Yep. Reset the top, because if we forget to do that, then if we push another value onto the stack, we're going to get another node over here that's pointing to this thing, and this is still going to be pointing to the top. So we should not forget to set the top equal to t. That resets this pointer so that it goes to here. Okay? Good. So that's how you push something. And the other thing you do with stacks is you pop. You don't specify what gets popped. It's always the top of the stack. And so what does that look like? Yep. So somewhere in there we'll want top equals top dot next. So that means we're going to have the top point back to this second node that was on the stack. But before we do that, we'll save, I don't know, whatever you want. Let's call it a node. T is equal to top. We change the top, and we should return t dot x. Okay. So we save this node. We reset the top to here. It is important that we save it, because once we reset the top to here, this node is lost if we haven't saved it some other way. We saved it in this local variable t. Now again, this thing works, looks like it's supposed to. And when we return x, the value that's stored in this node. The reference t is lost, is gone now. So this thing is just dangling off here all by its lonesome. Nothing refers to it. The garbage collector will clean it up at some point. If you're working in a language that doesn't have garbage collection, you would have freed T here. So in a language like C, you would call free. In C++, you would call delete on the value of T before you return. Otherwise, that piece of memory would be gone, lost to the program. Okay, easy enough? So how long do these operations take? Yeah, I mean, they're dead simple, right? This is just a few instructions. The one that hides a little bit of trickiness is this new node has to somehow ask for some fresh memory somewhere. But other than that, it's constant time. And this, if it's implemented well, should also take constant time. So push and pop are easy. So a stack we can do with a singly linked list. No problem. Well, how about a queue? So a queue is something where we want to be able to add at one end and remove from the other. So again, if we have a singly linked list, we'll have some structure like this. And this seems a little bit more complicated than a stack because, if this thing gets big, then we somehow need access to both ends. We need to be able to add to one end and remove from the other. So somehow we'll need to keep pointers to two things. One is here, and the other is here. Now the question is, which end do we add from and which end do we remove from? Or does it matter? Yep. What are you calling the back? A successor? Yeah. So let's call this the tail, and let's call this the head. So, the tail of the lineup, the queue, the head of the queue. So when someone is leaving the queue, they're going to leave from the head. When someone arrives and has to get in the lineup, they're going to be at the tail here. Okay? And so with a queue, we need to do two things. We need to add. And how does that work? So we want to add at the tail. Yep. So we have something like T is a new node containing X. So we created this new node, which is referenced by a local variable T, contains the value X. And now we want to make this last node point to this node. So that looks like tail dot next is equal to point to T. And then what? Yep. And then tail is equal to T as this go to there. Is there anything that we may have forgotten about here? Yep. Sure. Let's say a new node creates a new node with a default value like it does in Java. So Anything, any maybe edge case we didn't consider? What's that? Yeah. What if we, I mean, we usually start with an empty data structure. So what does an empty queue look like? So let's draw a picture of an empty queue over here. It has tail and head. What do? What are they? They're both set to null. So if I run this procedure on an empty queue, I create a new node t, and then I say tail.next equals t, this is a null pointer exception, right? I tried to set null.next equal to t, well, null is an invalid pointer. So how do I account for that? Yeah. Yeah, so the only time that the tail should be null is if the list is empty. So we can ask, you know, if the list is empty, which is the same thing as asking if tail equals null, well, what should it look like in that case? Yep. Yeah. Then you do something like head equals tail equals t, and then what? Then we do the rest of the code? Nope, because if we run the rest of the code, so far in this case we create this new node, we set head and tail both to t. If we keep going and run the rest of this code, then we'll set tail.next equal to t, and then this thing will point back to itself. That's not good. We don't want that. So we should, you know, put some logic around this. You know, in this case, this is what we do. Else, this is what we do. Okay. So it's not difficult code, but there is a special case you have to consider here. The usual picture that you draw is not always going to work. Okay. All right. Now what if I want to remove from a queue? So that means I want to take this thing off of the head. So what is the well, tell me what to do. Yep. So somewhere in there we'll want head equals head.next. That's going to take this pointer head and jump it over here. Okay, that looks good. Before we do that, usually when we remove, we want to return what it is that we're removing. So we can say node t is head. At the end of this thing, we're going to do something like return t.x. Anything else we need to do? Yep.
Account for the case where it's actually this.
Well, I would say that you don't have to care about the case when it's empty, because then someone is asking you to remove from an empty queue, and you can happily throw an exception because they asked you to do something that's illegal. So if that makes a null pointer exception or something happen here, I don't care about that. But there is a special case. Yeah? When there's only one thing, there's no head.next. Exactly. So there's always a symmetry between adding and removing. And usually it's like adding has a special case when there's nothing there, and removing has a special case when you're removing the last thing, because that takes you to the case where there's nothing there. So we have to worry about the case where we are trying to remove the last thing. So in that case, it looks like this. Okay, so what do we do then? Yep. Yeah. So if it looks like this, and we do head equals head.next, that's this line here, then head becomes null. And that's our clue that we've just removed the last item from the queue. So if head equals null, then, well, we don't want tail still referring to this thing. So we do tail equals null. That makes it look like this. And that's the way it's supposed to look when it's empty. Okay? So there's somehow two cases for remove. It's different when you're removing the last element from the list. There's this extra thing you have to do. Okay? So far we can do, with the singly linked list, we can, and this representation, we can add at this end. We can remove from this end. But we also saw actually with the stack that we can also add at this end. Right? So this was called top in the stack version, and we added at this end in the stack. So actually, we have, we can do adds at this end. We can do removes at this end. And we can do adds at this end. So we're only one operation short of having a full deck here, which would allow us to also remove at this end. Now it's tempting to try and figure out how we can get that last operation, but there's no way to do it with a singly linked list. Because the main problem is, in a singly linked list, when you remove the last thing, in order to do these adds quickly, we needed to keep track of the tail, right? That's what we were doing, keeping track of this tail pointer. So if I remove this, I'll need to update this tail pointer. Well, what should it be updated to? It should be updated to this node. Now, how would I get to this node? Yep. Yeah. In this graph, there's only, starting from what's in our data structure, which is tail and head, there's only one way to get to the second last node, which will become the last one if we're going to delete it, and that's by starting at the head and walking through all these intermediate nodes. So you can get 3 of these 4 deck operations to work in constant time, but if you want that last one, it's going to take you order n time. So that's where we get unhappy with a singly linked list. And then, of course, what's the solution? If you want all of those operations, yeah, a doubly linked list. So in a doubly linked list, you have nodes. Let's distinguish them. We'll call them DL nodes. They have some data X. They have a DL node reference next. Actually, I'll write it prev, and another one called next. When we draw them, the nodes have those three parts, and we draw them in the convenient way for us. X goes here in the middle, prev goes here, and next goes there. And when we make a list out of these, everything points where it's supposed to. So if we want to link these in order, then the next pointers should all point to the next one. And the prev pointers should all point back to the previous one. Okay. Good. So that is what our nodes look like and how they should be linked together in using these next and prev pointers. Now what does our list look like? What should we store? Yep. Okay, so the first try for a doubly linked list would be you do what we've been doing and you store the head and the tail. Tail refers to the last node in the list, and head refers to the first node in the list. Okay. And if you do that, you're going to run into trouble. So let's try and write, for instance, so now we won't think about stacks and decks and queues, adding and removing at the end, but we'll think about just adding or removing anywhere you want. So these things have indices 0, 1, 2, 3. And so I want to, I want to be able to add and remove at any index or change any value. So for example, well, let's try and write a simple piece of code. Get node I should return the node at index I. No. Next being null is not the trigger for us, for anything in this case. Yeah? Sure. So you're suggesting that we start at the, let's say here, and we walk until we get to the ith node? It kind of depends what I is, right? Yeah. Yeah.
So we should first check and see if I is less than or greater than, like halfway, or like halfway between our.
Yeah. So we probably want a couple of things in addition to head and tail, which we may rethink shortly. We also want to keep track of the number of nodes in the list. Otherwise, we don't really know how I compares to the beginning or end. And we can also do bounds checking with that. Then we do something like, the easy case is, let's say, if I is less than n over 2. That means the thing we're looking for is in the first half of the list. Then we should probably start at the head and then work our way forward. So we do something like node u is equal to the head for j equals 0, j is less than I, j plus plus, u equals u dot next. Okay? So we count up to I minus 1, moving u forward in this list until we get, and if we do that right, which I think I've done here, you can check it, for instance, for I equals 0. We'll finish with u pointing at the ith node. Okay. Then we return u. So that's terribly indented. And otherwise, if that means I is bigger than or equal to n over 2, then we should start at the back. And we want to count backwards the appropriate number of nodes. So let's say for j is equal to n minus 1. So we start here at position n minus 1. We'll continue as long as j is bigger than I. And we're walking backwards, so we decrement j. And we say u equals u dot. And return u. Okay. So we either start at the front and walk forward, or we start at the back and walk backwards. So how long does that take? In the worst case, if I is n over 2, it takes n over 2 steps. What's the way we've been writing this as in a more general form? No. Yep. Yeah. So, in the more general way of writing this is it depends on both n and I, and it's the minimum of I and n minus I. It's I if n is if I is in the first half, so if I is smaller than n over 2, otherwise it's n minus I if it's in the second half, and you'll see that that means you're taking the minimum of those two quantities. Okay. All right, good. How about if we want to do something simple like add a new node so that it takes over index I? So I want to add a new node somewhere at some specific index in this list. What's the first thing you should probably do then? Yeah. You can do bound checking, sure, but I mean, you do some bounds checking if you care about your users. But then what? Yeah. Get a node around I, because you can always get before and after from the pointers that thing stores. But we should get to the place where we want to do the insertion, right? So we might do something like u equals, or maybe w equals get node I. We already wrote some code that goes and finds us the node at position I, so we can go get it. And, well, we should probably make u as a new node once we want to insert. it contains the value x. So if we look at what we're doing here, let's take I equals 2. So far, the code that I've written there will do something like walk through this thing, find this thing called w, as well as creating a new node called u that contains x. And now we want to splice x into this list so that it appears at position 2. So that means it should come after y and before z, right? So, can we write the code to do that? Who wants to give it a shot? Yeah. I'll let you go. W dot previous dot next is equal to u. Now, when you're doing this, if you're trying to reason about this code, it's very important to go back and update the picture immediately after you write every single line of code. So w dot previous dot next is equal to u. So w dot previous is this guy, and his dot next is this thing. So now that points to u. That's good. That's where it's supposed to go. Next. U dot next is equal to w. U dot next is equal to w. All right. W dot previous is equal to u. That changes this pointer to u. And then finally, u previous is equal to what? Yeah, so we lost this node when we did that. So you have to be really careful when you're writing these things because things like this happen. So when should we have done that? Yeah. So u dot previous should be equal to w's previous, and then w's previous can then be equal to u. So wind back the picture for a second. We had this. So we take u dot previous and we set it to w dot previous. That points it to there. And then we take w's previous and we point it to there. Good. So that looks correct. Is it? Yep. Sure, n plus plus. Anything else? Yeah. Well, the indices are implicit somehow. So now if we walk this list, we'll see 0, 1, 2, 3, 4 in that order. So that they're implicit. If you start at this end, they start at 0, and if you start at this end, they start at n minus 1, and we have both of those quantities in hand. So that's not an issue. Yeah? Yeah, the edge cases. So this already was like somehow the easy case. We're inserting, and the thing we're inserting is nicely in the middle. It doesn't have any boundary issues. Things we have to worry about. Well, things we have to worry about could be, for instance, w dot previous. could be null. If it's W is the first element in the list, then there's no previous element here. So that would crash the code here. And what else? What if we were trying to insert at the end of the list? So now that means actually we're trying to insert at position n, and our getNode function returns this thing, which is actually doesn't make sense. In fact, already getNode has a problem there. That's a problem. So this won't work if we're inserting at the end. In fact, getNode will crash because it will try and walk off the end of the list. It'll give us, well, it just actually won't even make sense at all. It'll return us this thing, which is not what we wanted. In fact, in that case, we would end up doing an insertion before the last element. Okay? So there's these border cases. And actually, they get kind of hairy and super messy. And don't forget, there's not only that, but if you're inserting at the end, well, then you also have to update tail. And if you're inserting at the beginning, then you also have to update head. And so this gets hairy quickly. And you know, if you're inexperienced and full of energy, you can make this work eventually, but it's with a lot of debugging and little bugs that only show up after you test some weird cases. Eventually you get it to work. If you're older like me, you have learned a trick, which is to avoid all of these edge cases. And the way you do that is rather than storing head and tail, you store something called a dummy. Okay, and the dummy, you can think of it as being upside down. So this would be the previous node. This would be the next node. There's no data stored in dummy. This thing is called the dummy. And the next node, the node that comes after the dummy, is the, but now you run into similar problems that you run into with arrays, and that is, well, sort of inserting into the middle in an array is kind of expensive, unlike a linked list. Once you can find the place you want to insert, inserting to a linked list is easy. It was just those 4 lines of code. The hard part was getting to the location. So, you know, what can you do about this? Well, so let's look at this structure a little bit and see what kinds of things we can say about it. So I have a doubly linked list. Its nodes contain blocks of items, and I'll say that inside each one is an array. In fact, I will put in here an array deck that can hold at most b+1 items. Okay. So now, I mean, let's start from the beginning. Suppose I want to get, let's just say the ith item in this list. So remember now, this looks like, this is the 0th item, the 1th, the 2th, the 3rd, the 4th, the 5th, 6th, 10. Well, actually we don't know. It depends what's in here. Let's say there's 9. and so on. So counting this way. So how would I get that? So what if I is less than 9? Yep.
If all the array decks are the same size, you use like a log function to find out how many times and that's how you get which array deck you need, and then you can scroll inside.
Yeah, so if they're all exactly the same size, then you can just use integer division to know which one you want. So you take I and divide it. If they all had exactly b plus 1 elements, then you would take I divided by b plus 1 and the floor, and that tells you which of these things you need to go to, right? But even if they're not all the same size, since you can't go directly there anyway, you have to walk through all these things anyway, you can just keep checking. You say, look, here this thing contains elements with indices 0 through 9, right? So you can ask, is I bigger than 9? If so, then I should keep walking. But if it's less than 9, then I can find what I need here. Then you just go to the ith element in this list. And if I keep walking, then I start here, but I change my value of I to be I minus 9, the number of elements that was in this list. And now I ask the same question. Look at how many elements are in this array deck. Is the new value of I that I'm looking for bigger than that, or bigger than or equal to that? And then if so, I keep walking. And if not, then the thing I'm looking for is in here at position I. So that's easy to do. And actually, if these arrays are quite full, so actually we'll maintain a little invariant here. Every list node, which remember is an array deck, except the last one, contains at least b minus 1 elements. Okay? So that actually means that it contains every one of these things except the last one, which might be partially empty. It contains either b minus 1, or it contains b, or it contains b plus 1 elements. So they're almost all exactly the same size, just off by at most 2. Well, and so then, actually, if you use this, this is the way you look for the ith value, well, then you can get to the ith value in time that's O of I divided by b, or 1 plus I divided by b. You don't want things too close to 0. So, right, because each time you take a step here, you're jumping over at least b minus 1 elements. And jumping over b minus 1 or b elements doesn't change the running time. So, as long as b is big, then the difference between divided by b and divided by b minus 1 is not much of a difference. Okay? So I can get to the ith value in one of these things in time which is faster than order I, which is what you have in a normally linked list. In fact, the speed up is about a factor of b. Any other speed up here that I could do? This is a doubly linked list, so is there another way I could find the thing I'm looking for? Yeah.
From the back end or the opposite end?
Yeah, if we start at the tail, then we can walk backwards. And then we're counting down from n minus 1 down to I in steps, except for the first step, which could be a small one because this may not be very full. But after that, it's in steps of at least b minus 1. And so that if we start from the other end, is 1 plus n minus I over b minus 1, which, by checking it to see if I is bigger than or less than n over 2, means we get the minimum of these things. So get I can be done in O of 1 plus the minimum of I, n minus I, divided by b. Okay. So this is faster by a factor of b than a doubly linked list, getting a particular node. All right. What if we want to add something to one of these lists? So I decide that I want to add, at position I want to add the value x. So I use some version of getNode, and I find that position I in the whole list is right here. So it should go right here in this array deck. So I would like to insert it there. And if this deck is not full, that's all I do. I insert into this array deck. How long does it take to insert something into an array deck whose size is at most b plus 1? Yep. Yeah, the minimum of, it's not really the original I now, it's whatever happened when you subtracted the sizes of all the other things from the original I. So it's hard to relate that to anything, but it's not more than b, for example, or b over 2, in fact. So when I add, I have to do this. I have to find the node that I want. And then I need to insert into an array deck, which I can do in O of b time. There's only one problem. What if this thing is full? So I can't add into this thing anymore because it's completely full. It already has b plus 1 elements. So let's focus in on that picture. I'm trying to add to this big list. I'm trying to add into this block, but it is completely full, meaning there's already b plus 1 elements here. I'm trying to put my element there. So what can I do? What's my fallback plan? Yep.
You grow the array?
Nope. I want all of these things to be the same size forever. So I don't want to grow them. Yep.
You follow with stop next?
Yeah.
It's like,
So I look at the next guy. And if this is not completely full, so if there's a space here, right, remember there's either going to be b minus 1, b, or b plus 1 things here. If there's b plus 1, I'm in trouble. But if there's fewer than b plus 1, then I have space. Well, then I can just do the easy thing. Take the last element out of here. And this is a deck, so I can stick it on the front of this thing. So I remove the last element from here, stick it on the front of this thing, shift these guys over. There's not even b of them. And that leaves me room for I, right? So if this guy's neighbor has any free space, we can just give one element over to this neighbor. That frees up a space here where we can store the element we're trying to insert. What if his neighbor doesn't have any free space? Because there's b plus 1 things here. And we check the next neighbor. And if there's a free space there, we're happy. We can just take the last element from here, add it to here. That frees up a space in this thing. We take the last element from here, add it to here, and then we're good to insert this thing. Okay? These things are decks, so it only takes constant time to move something from the end of one to the beginning of the other. Good. But, you know, if we're really unlucky, this goes on again. This is still full. And again, this is still full. So do we get into a situation maybe where we have to go right to the end of the list? We could go like right to the end, yeah. And eventually, you know, do this. Then we get to the end. And, well, even if that one was full, then at least we know what to do. We can add a new node at the end. But actually, we shouldn't do it for that long. We shouldn't go all the way to the end of the list. Instead, let's do this for a while. So this block, first block we tried was full. The second block we tried was full. The third block we tried was full. And let's go until we have seen a total of B blocks. So call this block 1, block 2, block 3, block 4, up to block B. Okay. So now we've seen B blocks. They're all full. That means each one contains exactly B plus 1 values. Okay. So now we have B blocks. Each contains B plus 1 values. What could we do with that? Now, something wonderful happens, which is there are no more edge cases anymore. Every node has a successor. Every node has a predecessor. You don't have two special variables, head and tail, that you need to update, because those variables are now what those used to be. These are the next and previous things of dummy, but the code for inserting into the middle of a list updates those already for you. Okay? So you never have to worry about these things being null. This code here works great. The only issue we need to look back is revisit this getNode function. So we will start with, so this started at the head, right? So in the first thing, if we're in the first half of the list, we start at the head and we start counting forward. So where should we start now that we have this representation? Yep. Not tail. Dummy dot. Dummy dot next. Remember, dummy is upside down, so its next node points to the first thing in the list. Okay. So that's good. That'll get us anything in the first half. Here, we started at the tail. Was that such a good idea? I mean, we could do that, which would be like starting at dummy.prev. And that will get us the ith node in the list for any value of I that's bigger than or equal to n over 2, and that's less than or equal to n minus 1, which is what this thing is. But the add method, sometimes you want to add at position n. So you want to append to the end of the list. So in that case, what does it make sense? Which node is at position n? The dummy. So these are at positions 0 through n minus 1, and then at the end is n, the dummy. So instead, we should maybe start at the dummy, and we'll count backwards, not from n minus 1, but from n, and we'll count backwards until we get to where we want to go. That way, if somebody asks us for the nth node, we start at the dummy, and we don't count anywhere, we just stay at the dummy. Now this code for insertion that we wrote here, it's kind of blind, right? There's only two nodes that it cares about, that it actually touches. It touches the node that's coming after the thing we're going to insert. So let's say I wanted to insert at position n. So this would be the W. We'd create a new node U. And that code correctly splices U in between W and W.prev, which is exactly where we want it at the end of the list. Nothing weird happens there. Similarly, if we try and insert at position 0, then this becomes our W. And we create our new node U. And that insertion code splices U in between W and its predecessor, which is the dummy node there, which is exactly what we want. It puts it as the first node of the list, the one that comes, the one that's dummy.next. So you don't have to do anything special to the insertion code once you create this dummy thing. It's a real time saver. Okay. Any questions? Yeah. How do you do w.previous.next if you're adding to the end? So if you're adding to the end, this is your value of w. So the dummy is the w. So w's previous value is this guy, and his next value is pointing back to dummy. So this is w previous next is this thing. So look at the first line, which says w.previous next equals u. That takes the last element in the list and has its next pointer point to u, just like it's supposed to. And then follow the rest of the lines, and you'll see they do exactly what they're supposed to do. Because this code is blind to what's happening in the list. There's basically only 3 nodes involved. There's the w, there's whatever starts out as w.previous, and then there's the node u that you're inserting. This code doesn't even care. It doesn't care if one of these is the dummy or not. It's not a problem. In fact, here's something slightly mind-bending. It doesn't care if both of these are the dummy. So this code will work even if there's nothing in the list except the dummy, and the dummy has 2 pointers back to itself. So it'll correctly update everything so that this thing appears as the only thing in the list. So there's no special cases at all. Removing the last node from the list, adding the first node to the list is all fine as long as you have this dummy. Okay. So that's probably the most useful thing I'll tell you about linked lists is these dummy nodes simplify things incredibly. And even you could even use this, for instance, for the stack implementation. It can be nice to, instead of having a pointer called first, you just have a dummy node, the thing that's before the top. Then there's, again, no updating the first pointer. Okay. Any questions? Yep.
Does error, does indices and bounds check
No, in fact, the nice thing about this list, depending on how you want to interpret it, is that you can, you can even say, you can ask me for the index, any node of any index, whether it's negative or positive or bigger than n or whatever. It just means you walk around the list a few times to get there, or you walk backwards around the list a few times. If that's what you want out of it. Officially, if you're trying to implement the Java list interface, well, it forbids you from accessing negative indices and accessing indices bigger than or equal to n. But there could be scenarios where it's actually useful to walk around this list. Okay. Yep.
What's stopping us from implementing a deck using a singly linked list, but an additional pointer that points to one before the tail? Because if you have n equals like n equals 0 or n equals 1, all the
So you're talking about something that looks like this. So when I had only the tail, the difficulty was that when I delete the last element, I have no good way to update the tail. So now you say, I do have a good way to update the tail. I delete the last element, and now the tail becomes the tail-ish. But what happens to the tail-ish?
Oh, shit, okay.
Yeah. So yes, you can store an array of pointers to the nodes in the list, but you see the problem. Yeah. Okay, so that's the basic linked lists. And I'll show you a little trick today. So a few things about linked lists. In Java, you don't see it so much, but in closer to the bare metal programming languages, they tend to be slow. So an unfortunate thing about computers these days is they have really fast processors and really slow memories. And so they've got this giant memory that's measured in gigabytes. And when you allocate list nodes, I draw them nicely in a line like this on the board somehow because that's the way we think of them. But they can be, popping up in all kinds of places in memory, all over the place, And this might be the order you get. Whatever, some crazy thing like this. So this action of following a pointer from here to here can be expensive. These things can be very far apart in memory, and that actually ends up costing a lot. Very different from an array, where if I'm trying to get from one list node to the next, all I'm doing is moving to an adjacent memory location. In fact, it's most likely that there's a whole chunk of memory here that when you looked at this node was brought into close to the processor, and now this is readily available, unlike the situation here. Okay. So these things can be slow, linked lists, and not only slow, but they can be wasteful of space. You have one data item and you have two pointers. So that's already not a good sign. So the question is, what can you do to make these faster and use less space? And the answer is, well, you can mix them with array-based structures. So if you want to save some space in a linked list, you make your nodes look like this. So this is your prev. This is your next. But instead of storing only one item in a node, you store a whole bunch of items. So let's say you give yourself in a node an array whose length is b plus 1, where b is something biggish, 20 or 40 or 100 if you like. And then, most of the time, adjacent list items will be close together. They're mostly beside each other in these arrays. Occasionally, you have to jump from one of these super nodes to another one. Okay? So you get a structure that looks like this, right? So I don't know. Here my value of b is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there could be 20 items here across these two things. And instead of storing 20 nodes, I'm only storing 2. Instead of having 40 pointers for prev and next, I only have 4 or so. So you can see that this saves space. And well, they're all of size. They all have a capacity. So they're array decks with a fixed size array of size b plus 1. And we know now that they're full. Otherwise, we would have found one that is not full, and we would be done by this point before we got to these b blocks. So now we have b blocks. Each one has b plus 1 values. They're all full. It's looking really tight, and that's not a good situation for this data structure. So let's just add one more block. So we add one more block. So now we have b plus 1 blocks. So I'll insert a new one here. It's completely empty. So I just created this whole new completely empty block. Now I take everything that's in these b blocks and I spread it evenly among the b plus 1 blocks. So at the end, what does that look like? Well, that means at the end, every one of those blocks, I'm not creating any new elements, every one of those blocks now contains, instead of b plus 1 things, it should contain b things, including the new one that I just created. This contains b things. So that takes a fair bit of work. The work that takes is on the order of b squared. But at the end, now I have all these blocks that are each have a free space in them. And now it's easy to finish my insertion. This one has a free space in it. I can just put this value I there. Okay. So it looks like if I analyze add, let's see what the cost is. So I first have to get the thing that I'm looking for. So the cost of add is first finding the thing that I'm looking for, and then I do this search through these blocks until I find one that can accept my I, accept the thing or that has a free space. So that takes at most b steps to find that thing if it's there. Then I do shifting, one element from this block to that block, one element from that block to that block. That's at most b steps. And then I do an insertion into this thing of size b, which also takes order b time. So far, we're up to 1 plus the minimum of I n minus I over b. And then we get Occasionally, we just don't find a block that's ready for us. So we don't find any empty block, and we have to do this crazy thing where we create a new block and push everybody else into those blocks. Okay. So then we get this b squared in our running time. But I'll highlight this and say that this only happens sometimes. Okay. So we're not going to get into too much more detail about this, and I don't want to continue this next class. But the short version of the story is this thing here, this b squared, actually we can argue about it using exactly the same kind of amortized analysis we've used before to show that this doesn't happen often enough. And in fact, over a sequence of n operations, this only happens n over b times. A similar thing happens with insertion and, with removal. And so in the end, you get a data structure whose amortized running time is this, and whose wasted space is of n over b. And you can pick any value of b that you want here. So you can take b to be equal to 1,000, in which case you're only wasting, if you're storing n elements, about 2,000 pointers. And your searches over a regular linked list are sped up by a factor of 1,000. Insertions have this extra 1,000 constant. Okay, so we'll leave it at that for today.